we're lucky because it's so easy to get him here, because he's at Stony Brook and has a sort of shared appointment with Stony Brook and CCA, where he leads the gravitational wave astronomy group, I suppose you would call it. And I was just asking about the prehistory, and he's been in LIGO for many years, because before being at Stony Brook and CCA, he was in Birmingham in England, which is one of the long-time early investors, let's say, in LIGO. And then before that, you were at Northwestern, where people have been there, and so on. And so it's really an honor and pleasure and privilege and good deal to have you here. Thank you so much.
Thanks for the introduction. This is, yeah, it's a lot of fun to be here, even if the trip is short. It's great to visit. And I will say, partly because I'm in LIGO, as I was just explaining to Glennis, this is a QR code which will take you to links to these slides. And partly I do that just because it's fun, but also I do that because many of the papers that I refer to will be Abbott et al. 2016 or 2017. LIGO publishes with an alphabetical author list. So which of the 50 LIGO papers from 2016 am I referring to? Click the link. All right. Yeah, so as Glennis mentioned, I'm in the LIGO collaboration. What is LIGO? Laser Interferometer Gravitational Wave Observatory. If you want to observe electromagnetic waves, what you do is you put some charges somewhere and you let the electromagnetic field push them around. If you want to observe gravitational waves, what you do is you put some masses somewhere and you let the gravitational field push them around. That is rather more challenging technologically than detecting electromagnetic waves, because gravity is weak and the types of pushes and displacements that we're talking about from gravitational waves are infinitesimally tiny. But you can do very precise metrology, distance measurements, if you use an interferometer. So LIGO is such an interferometer, in fact, two such interferometers. There's one up here in Washington State on the Hanford Nuclear Reservation. There's one down here in Louisiana. And they are, at root, Michelson interferometers with a bunch of fancy optics. A laser shoots here into a beam splitter, goes down to perpendicular arms. The light bounces off of a free swinging, it's actually not free swinging, but never mind the details. A free swinging mirror here that's disturbed by the gravitational field comes back, recombines destructively if the mirrors are not shifted by a gravitational wave, and constructively, if they are, comes out here and is read out before the effect. Okay, that's the basic idea. The technology there is really fantastic. It involves things like squeezing, so the Heisenberg uncertainty principle is exploited to reduce phase uncertainty in certain parts of the frequency range, and amplitude uncertainty in others. So that's fun, but that's a whole other talk. What I want to show you here is just if you let the interferometer run in the year 2016, so a while ago, and you measure the output here at the photodetector, you're recording the stretching, the just free swinging noise in the interferometer, no gravitational waves present, or no measurable gravitational waves present. And the spectrum you get, strain, which is just the fractional change in this length, versus frequency looks something like this. There's lines. That corresponds to various modes of oscillation in the interferometer. Some of them are mechanical, some of them are optomechanical. But in bulk, there's a sort of sensitivity to say a strain of 1 part in 10 to the minus 23. So the LIGO instrument is 4 kilometers long. So 4 10 to the 3 meters times 10 to the minus 23 is 4 10 to the minus 20 meters of stretch, which is rather a small number. Strain sensitivity of 10 to the minus 23 at frequencies of about 100 hertz. And if you do a little bit, oh yeah.
A dumb question. There's a peak at 60 hertz, of course, and I guess 120. What are these things that the interferometer is seeing at other frequencies?
So I happen to know some of them. Humans know most of them, and some of them are as yet really undetermined. But these ones right here at around 300 hertz have to do with violin modes in the suspension wires or the fused silica strings that are holding the mirrors up. The 60 hertz you've identified as the power grid coupling into the instrument. There's another one at 120 hertz, which is the first harmonic of that, and so on and so on. I think, not all of these lines are of known origin, but they're all that kind of thing. And they move around with time, they drift a little bit, their amplitudes change from time to time. You shut the instrument down, replace kit, turn it back on, they're in different places and so on. So we treat this as an empirical measurement of our noise level. Let the instrument sit, measure it, and then we use that in our analysis.
And that's at some level, the time average noise, or the
That's
short
right.
time noise is a different story that you'll have to tell us about.
Yeah, there are pops and glitches and things that I'm going to sweep under the rug, but we do have algorithms that are designed to deal with those. That's primarily an issue for detecting signals. Right, so if I told you that I was looking for gravitational waves that are near 100 hertz, you could immediately, if you sat down for a little bit and just calculated like Keplerian orbital frequencies of objects when their Keplerian orbital speed is near the speed of light. So we're talking here about like black holes orbiting close to their Schwarzschild radii. The frequency of the gravitational waves emitted by a 10 solar mass binary black hole peaks out at about 200 hertz. So the mere fact that we are most sensitive here in the hundreds of hertz tells you that we're listening for compact objects of sort of solar mass scales. And now the fact that our strain sensitivity is something like 10 to the minus 23, if you think about gravitational waves, or any wave really, waves propagate and conserve energy. The energy in a wave is proportional to the square of its amplitude, harmonic oscillators. So therefore, the square of the amplitude of the wave has to fall off like 1 over r squared. It's energy conservation, right? It's the inverse square law, it's familiar. So the amplitude of the wave falls off like 1 over r. Gravity, though, is described by strain. It's a relative stretching. It's a dimensionless quantity. So to describe the wave, I need some, length dimension thing to put there on top of the r to make the strain dimensionless. And in gravitational problems, the length dimensional thing that I have is the Schwarzschild radius. So the amplitude of the wave is some order 1 factors that have to do with, the distortion of space-time near the Schwarzschild radius as these objects are merging, divided by times the ratio of the Schwarzschild radius to the distance to the source. And so if you plug in a 10 solar mass black hole and you put it at 1 gigaparsec is about 10 to the 23 Schwarzschild radii, its strain amplitude is right here at the level we can detect. So we're looking for solar mass scale compact objects that are gigaparsecs away, right? A good fraction of the observable universe away. And that's exactly what we found. GW 150914 was the first detection. It happened the fall of 2015. In the observing run that we did from 2015 to early 2016, and then another observing run in 2017, we found 10 binary black hole mergers and a binary neutron star merger. They're shown here in terms of chirp mass, which is a combination of the 2 masses in the system, but it's just a mass parameter. You can see here tens of solar masses, and the distance to the objects is 1 or a few gigaparsecs, as I just described. These are all the black holes that we found in this first observing run, up here conveniently as redshift, by the way, if you like to think of redshift instead of distances. That little blip down there is the neutron star merger that we saw. So this matches what you would expect. It's detectable in LIGO. This is our gravitational wave transient catalog number 1, published in 2019. All of these systems, if we look now, instead of in this chirp mass parameter in mass space, M1 and M2, they are all pretty consistent with being equal mass mergers. 2 black holes or the 2 neutron stars have the same mass, maybe 2 to 1 mass ratio, in extreme cases 3 to 1, but not really 4 to 1 or higher. that suggests that most of the merging black holes in the universe are equal mass, though that's a little more complicated to assess because these signals are much louder than those signals, so we have a selection of bias that's going on here. But it is in fact true that most black hole mergers occur at near equal masses. Moving forward, the third LIGO observing run detected something like 40 black hole mergers.
Is there some reasons why all mergers happen around the mass?
There are.
It was a little quiet.
Oh yeah, the question
why
was.
the mass ratio is close to 1 most of the time.
Yeah, why are mass ratios close to 1 most of the time? That's not a necessary fact, but there are binary astrophysics reasons why two massive stars that grow up together and interact with each other will most easily survive to produce merging black holes if they're close to the same mass, having to do with stability of mass transfer in unequal mass situations and various other evolutionary considerations. So it's not a surprise, but it also didn't have to be that way. 2 to 1 would have been fun in terms of binary theory. Okay, so what happened? This was sort of about a year of total integration time in the instrument. This was 6 months of integration time. I guess the universe just got busy. That's not what happened. What happened is the thing I mentioned before. We're sensitive to amplitudes. Right? We are better than astronomers. Astronomers with a telescope make a photon bucket. Right? The photon hits the CCD, is destroyed, and the energy is recorded. So they suffer from the inverse square law. We coherently measure, and we don't catch gravitons, we interact with them as they go by. So when we improve our sensitivity by a factor of 2, the most distant source we can detect moves out by a factor of 2, but the surveyed volume goes like the cube of that. We have 8 times more surveyed volume. So sensitivity improvements between here and here gave us about a factor of 8. That's a huge advantage for gravitational wave astrophysics, and we exploit it as often as we can. Okay, so this is the first 6 months of O3A. We had another binary neutron star merger. We had a whole bunch of binary black hole mergers. This is total mass and mass ratio. And we even saw some neutron star black hole mergers. So the combinatorial catalog of compact objects is now complete. Another 6 months of running and you get another 30 or so black hole mergers in O3b. And again, we're talking tens of solar masses, mass ratios near 1, maybe as much as 2 to 1, which is sort of here. We have 1 or 2 sources that are sort of in the neighborhood of 10 to 1. There's one here. There's one here. Okay, and a talk about the details of the catalog would be fascinating, but that's not quite what this talk is, so I'm gonna move on. But if you wanna ask me about some of those weird events, I'd be happy to talk your ear off later. We just finished the first 9 months of our 4th observing run last month in January. In those 9 months, we detected 81 sources. So the full catalog up to the beginning of O4A was about 70 sources. The first half of O4A, we've doubled that. We'll turn on again in March, maybe April, late March, early April, and with even some sensitivity improvements and get another 80 or maybe even 100. So we'll be talking at the end of 2024 about, of order 300 binary black hole mergers. LIGO will have a 5th observing run starting in a few years from now, 2026, 2027, in which we expect to maybe get as many as 1,000 detections a year.
What happened to those 11 retracted?
Those are the pops and glitches that I said I was going to sweep under the rug. This is part of, you can click this link, it'll take you to a site called GraceDB, which is our gravitational wave database. We try to engage the traditional astronomical community, so we try to announce the events as quickly as we can. And then later, if we determine that there was an instrumental glitch, we retract them. That's an optimization problem to try to get telescopes on scene as fast as possible. And typically, when we analyze the data offline, we find more than 81. There's some quiet stuff that isn't found as readily in these online quick search algorithms. We have to dig a little deeper.
Is the off time and on time just that you would run all the time except you have to do improvements, or does it actually cost a significant amount to run?
It's not terribly expensive to run. It does cost something. It's not free.
It's not like the LHC.
But it's not like the LHC. There's momentary downtimes, there's certain consumables, there's pieces of the experiment that are cooled with liquid nitrogen and so on that has to be replenished. Then these longer downtimes are sensitivity upgrades, which is almost always beneficial because, you know, the space-time volume we survey is a volume times a time. The time goes linearly, the volume goes like the cube of the sensitivity. So if you have to pick, you shut it off and make it better. Yeah. Okay. Right, so now I want to talk, we have now a catalog of order 100 binary black hole mergers. We're accumulating a few hundred more. By the end of the decade, we'll have thousands of these. What can you do with them? Many things you can do, but the thing I want to talk about, at least in this first part of the talk, is I want to do cosmology, cosmography, distance and redshift measurements with these black holes. Okay, in gravitational waves, the situation is almost the inverse of what it is in electromagnetic astronomy. In electromagnetic astronomy, it's easy to measure redshifts, right? You take a spectrum, there's a line, an absorption line, an emission line, whatever, it's in the wrong place. You get the redshift. It's hard, I mean, I'm not saying it's easy, but like conceptually, it just follows automatically. It's the distance part that's hard. You need a standard candle and you have to build a distance ladder in order to work up to that distance, or you need a length scale in the early universe, whatever. The distances are challenging. For us, it's the opposite. The distances are easy and the redshifts are challenging. And the reason the distances are easy is this is a constant of nature. C to the fifth over G is 3 times 10 to the 59 ergs per second, which is something like 1 million or maybe 10 million times a supernova luminosity. This is a standard luminosity. And it turns out that that is the luminosity that an equal mass up to factors of order 1, or maybe 0.1, something like this. This is the luminosity that an equal mass binary black hole merger achieves in its final orbit. Okay. It's big. This is a big number. GW 150914, if it had come out in photons, would have been brighter than the full moon, even though it was at 300 megaparsecs. You would have seen the flash in the sky. So this is a huge number. Which is great, means we can detect these events very distantly, but also it doesn't depend on the details of the source. The reason for that is this is relativity. A constant fraction of mc squared comes out, so heavier things have more energy that's emitted, but the orbital speed is the speed of light, so the orbital time is the light crossing time of the Schwarzschild radius, which grows with m. So the energy grows with m, time scale grows with m, the luminosity is a constant.
And then the mass ratio for some.
It does have an effect. To actually do this, we don't use this number, we do real GR. But effectively, all of our systems are standardizable candles. So distances for us are in the bag. It's the redshift that's hard. And the reason that's hard is the way that we measure the mass of our system is we look at the frequency evolution as the bodies march inward towards merger. And the heavier they are, the faster that frequency evolution is. The frequency is redshift. So we don't measure the true rest frame mass of our sources, we measure a redshifted mass. What we observe in the detector is a waveform that looks like it has a mass, m obs, which is the true rest frame mass times 1 plus the cosmological motion. Now, one way to do distance and redshift measurements is easy mode. You just combine the gravitational waves for the distance and the electromagnetic measurements for the redshift. That was famously done with the binary neutron star merger in 1708-17. That event was at like about 35 megaparsecs of distance. That comes from the gravitational wave part. Its redshift, okay, c times its redshift, effective recession velocity was in the 2,800 kilometers a second.
You know what, for some of the audience, it would probably be nice to give them a yardstick about 35 megaparsecs. Like this distance from us to Andromeda.
12 Kesselrons.
Sorry?
Yeah, it's 12 Kessel runs. No, it's so a parsec is about 3 light years. So this is 120 million light years. Andromeda is, of order a megaparsec away.
Or
Okay, so
nearest major
galaxies,
galaxy
yeah,
is-
galaxies are tens or 100 kiloparsecs, more than that in their dark matter halos if you care about that sort of stuff, but the visible stuff is all contained within, say, 100 kiloparsecs. The distance between nearby galaxies is of order megaparsecs. A big galaxy cluster might be 5 megaparsecs. So this is 35 megaparsecs. This is outside the local group of galaxies. The size of the universe is, of order 10 gigaparsecs. Okay, so this is quite local. The redshift here is 0.01. So it's not cosmologically distant, but it is far away from the local group and partaking of the Hubble flow. So in fact, the Hubble constant, right, the expansion rate of the universe is just the slope of this line. Okay. So this is the gravitational wave Hubble diagram. It turns out that the Hubble constant is, 70 plus or minus 15 or so from this measurement. So we're not exactly where people are in doing type 1a supernova measurements or, CMB measurements or galaxy correlation measurements or anything else, but we're getting there. This is the original Hubble diagram, and so hopefully it won't take us 100 years to get to the state that modern cosmology is in. However, this is a lot of fun because you get to work with electromagnetic astronomers, but this is also hard because you need an electromagnetic measurement. And black holes, which is our most numerous class of source for now, are made of gravity. They don't make photons, or at least except in exotic scenarios, they don't make photons. So what can you do with gravitational waves alone? Well, if somebody called you up on the phone and told you that the black hole you're about to see was 30 solar masses, then you'd be good to go. Because you measure this, and a dude just called on the phone and he told you this was 30, so now I can work out what the redshift is. Well, the universe is not that kind. Black holes come in a range of possible masses. However, this idea works if there are features in the mass spectrum. Right? If a black hole is more likely to be 30 solar masses than to be 20 or to be 40, then you can't make this measurement uniquely and perfectly every time, but if there's a preponderance of 30 solar mass black holes, then more of these are going to be around 30 than any other number. That lets you statistically measure redshifts for your population. And this is an old idea. It goes back to Chernoff and Finn from 1993. Taylor and Kerr wrote about it. These are all papers about doing this with neutron stars, which are all basically 1.4 solar masses. So you did actually get a phone call about what they are. But you can do it with black holes too. How do you do that? Well, you look for features in the black hole mass spectrum. So this is what passes for an old classic paper in the space of LIGO, Fischbach and Holtz, 2017. And this was a paper that was written, Maya wrote this around the end of the first catalog when we had 10 sources. And the paper's title is, Where Are LIGO's Big Black Holes? The first 10 sources, here's estimates of their masses. And you can see they peter out here at, maybe as much as 60, but no more than 60 solar masses. LIGO should have been able to detect 100 solar mass merger had there been one during this observing run. So evidently, mergers out here at 100 solar masses are much rarer than mergers in this 20 to 30 range. So Meyer, built a simple model where there's a power law black hole mass function that just cuts off and asked, where's the cutoff, right? Turns out the cutoff is at about 40 solar masses, 40 to 45. And this was already apparent with 10 sources. But life gets better as you have more sources. So we followed on and wrote a paper, Maya was also on this paper, that pointed out if you had such a cutoff, it behaves like an absorption line. Right? Mass is redshift. So here we're looking in distance and detector frame mass, redshifted mass space. And we built a simple model where we imagined there was a power law of black hole masses until there was some taper function that just sent them all to zero. Nature just doesn't make heavy black holes for some reason. And this is what that would look like with 1 year and 5 years. So the 1 year is these faint blue dots, the 5 years is the orange dots, of advanced LIGO at design sensitivity, getting about 500 sources a year. And this cloud of points here, you can see that as the distance increases, you no longer detect low mass black holes. That's a selection function. The low mass systems are quiet. They're hard to hear, so they drop out of the population. But you also see there's an edge here, an upper edge to the black hole masses. That's the absorption line. You're seeing, 40 solar masses is where it starts to taper in the rest frame. And as you go out to higher and higher redshifts, that appears at larger masses in your detector. So you can put error bars on these measurements and build a statistical model that finds where the break is. Where is that cut? And infers the edge, if you like, of the black hole mass function. Well, that is just a redshift versus distance curve. So the shape of that tells you about the cosmological parameters in your model, lambda CDM parameters, the Hubble constant, matter density, etc. And so another way to look at that is you are building a cosmology so that distance converted to redshift and then turned into a source frame mass makes the edge of the black hole mass function a constant mass. So you take this diagram, come up with redshifts that flatten it out into this diagram, and you're finding the edge. And that's sensitive to cosmology, so then you learn cosmology. So if you convert that to an h of z, right, an expansion rate as a function of redshift, here's the sort of median and 1 and 2 sigma intervals you get after 1 year of observations, 5 years of observations. After 5 years, you measure h of z to 3% at redshift 0.8. 3% at redshift 0.8, you can drag it back to redshift 0 with supernova. That's plus or minus 2 kilometers per second per megaparsec, which is cute because if the Hubble tension is still going when you've got this data in the can, you can answer. Okay, well that's great. This is a classic paper from classic paper from 2017. Time has moved on. We now have hundreds of sources. What does the mass function look like now? Here's some different views of the black hole mass function. So I'm going to focus on this one. It's a neat paper that Tom Callister wrote when he was a postdoc at CCA. It's called a parameter-free tour of the black hole distribution. So this is basically assumption-free, data-driven fit to the black hole mass function, 10, 30, 100 solar masses. This is the rate of mergers per log mass. And you see the edge that Maya found in the early data is no longer a sharp drop to 0 edge. We've seen a few high mass black hole mergers, but instead is a feature. There's a bump. There's an excess of black holes at 30 solar masses before falling 1 or 2 orders of magnitude in merger rate at higher masses. So this feature is actually better than an edge because there's an excess. There's more black holes here. We like lines better than just edges. But it would be maybe more comfortable if we could understand why this feature is happening. And we might understand why this feature is happening. So it has to do with the physics of massive stars. Okay, the progenitor stars for a 30 or 40 solar mass black hole are themselves 80 or 90 solar masses. These are monsters. And those stars can develop a carbon-oxygen core in the later stages of their evolution that is, 30, 40, 50, 60 solar masses. And this core is very hot. In fact, its kinetic temperature is coming within spitting distance of 511 keV. So in this core, it's radiation pressure supported. The photons are providing the pressure to support the core. And the tail of their thermal distribution is able to pair produce, right? When the photon is 511 keV, they can produce an electron-positron pair at rest. So as the temperature of the core increases over the lifetime, at some point, there's enough of a tail of the photons to start pair producing. And you go from a relativistic fluid, that's photons, to electron-positron pairs at rest. The equation of state softens. Right? Electron-positron pairs at rest don't have pressure compared to photons. So the core starts to collapse, and that ignites nuclear burning, explosive nuclear burning. From there, one of two things can happen. The explosion can be rather weak, and drive a shock through the star that just burps off the outer layers. And then the star returns to equilibrium with a cooler core. Eventually the core heats up again. You may go through multiple phases of these sort of explosive burnings. And that produces a softening in the relationship between the core mass and the black hole mass. Here at low masses, where you don't have this instability, heavier cores make heavier black holes. Once the instability kicks in, the heavier cores burp off more and more and more of the outer layers. The relationship turns over and reaches a maximum black hole mass. And then if you have a really heavy core, the explosion is so powerful, it blows the whole star up and unbinds it in a very luminous supernova. These are called pair instability supernova. This is called the pulsational pair instability. And that leads to a maximum in the black hole mass of somewhere in these models, somewhere around 45 solar masses. That doesn't quite match our data. Our data puts it more here in the mid-30s, but never mind, stellar astrophysics is a messy business. I don't know. But generically, when you see this kind of feature, there's a linear piece of the initial mass, final mass relation, and then a turnover. You will get a pileup, a bump, followed by a decay. And the reason is when this turns over, there's a finite range of initial masses that all map to the same black hole mass. That's the bump. And then there's a decay because it's hard to make black holes up here. So you can build simple parameterized models. Here's a paper with Jay Poulin, a very talented grad student at Caltech. Max Easy, he's a postdoc with me at CCA, where we made a very simple model for this of just like a linear turning into a quadratic going to 0. And if you put in a featureless initial mass function of cores, and you map it through this initial to final mass relationship, you get a nice bump followed by a decay. And the reason that's important is because this process is messy stellar astrophysics. Now the story I told you, 511 keV, there really wasn't a whole lot of detailed stellar astrophysics in it. So the hope is that this process is pretty robust across cosmic time. But if it's not, if the sort of features, the location of where the pulsations start, the width of masses over which pulsations occur, the amount of, star-to-star scatter in the output masses, all those features change, it changes the shape of the black hole mass function. So that gives us a sort of means of calibration or testing that this process that we're hoping to use for cosmological observations remains consistent across cosmic time. Like, for example, here, if the pulsations change the mass at which the pulsations start, so 33, 37, 40, 50, the peak shifts to the right and gets lower. If the maximum black hole mass changes, the peak, the onset of the peak, the rise spot stays the same, but the right edge of the peak moves to the right and it actually gets higher, right? These shape changes, which we can measure in the black hole mass function, can let us calibrate out the underlying astrophysics. Currently, we have some constraints on the shape of the peak. This is what the shape of the peak looks like measured after our order 100 black holes. We're expecting to get another order of magnitude or maybe more, so we'll get quite tight constraints on the shape of this peak, and we can check whether this picture is the right recipe, the right underlying astrophysics. There's another peak in the black hole mass function at 10 solar masses that I didn't talk about, but it's also useful for this sort of mass function cosmology. And in fact, if you use both peaks together, redshift moves them homogeneously. They both get multiplied by 1 plus z. Astrophysics does who knows what, so it's yet another calibration check. So if you put all those things together, and you fast forward, say, to the mid-2030s, when the next generation of gravitational wave detectors becomes available, that next generation of detectors sees gravitational wave events across the universe. Any binary black hole merger is within its horizon. The redshift at which you could see a 10-10 merger is like redshift 100. There aren't black holes at redshift 100 unless they're primordial. So you get something like 250,000 black hole mergers a year. You find these features in the mass spectrum, you use them to estimate redshifts and distances, You can place a constraint on h of z that looks something like this. This width here is a few percent in each redshift bin, right? So pushing out even to redshift 3. The little bars here, so the blue here is 1 month of gravitational wave observation, 50,000 black holes or something. The little green bars here are DESI. So a massive spectroscopic galaxy survey that's currently underway. And you can see the error bars here are maybe a factor of 2 better through sort of this critical redshift range as you go from matter dominated to dark energy dominated. So this can become a fantastic tool for precision cosmology as we go forward into the next one.
Can I ask, why does it stop at redshift 3?
That's just where the plot stops. Although cosmic noon is here. It's where most stars are getting formed. So at some point, the black holes taper off. We don't actually know terribly well high redshift star formation rates. That's one thing JWST might help disentangle. So this probably does not continue with this statistical power to redshift 6 because you run out of black holes. Certainly doesn't continue to redshift 12 because you barely made stars at redshift 12, but we're not really sure what happens there. If there are black holes there, we can detect them and we can use this to place some constraints on the expansion rate in that redshift range, which is a difficult one to reach by any other means. So that's cool.
Do you have any handle on the distance other than apparent mass?
There are several other possibilities. One is to take galaxy catalogs and match them up, cross-correlate black holes with galaxies, because the mergers happen in galaxies and you can measure the redshifts of the galaxies and then try to do that measurement. For neutron stars, there's yet another way, which is the neutron stars are subject to tidal distortions that measure the radius of the neutron star. And that gives you an absolute length scale, which lets you measure the Hubble constant. It's not completely clear which of these are going to dominate in the near universe. In the distant universe, this mass function trick is pretty much the only thing going, because galaxy surveys peter out somewhere, out here, even in the next decade. Neutron star tidal measurements can only be made for nearby loud neutron star signals.
So then if there are a bunch of primordial black holes, that's like a background because they wouldn't obey this mass function.
Yeah, it's a background. That's okay as long as their merger rate doesn't totally swamp. I don't know what you think their merger rate is at redshift 6.
I don't know, I do.
Yeah, I don't have any idea, but this is 100 per cubic gigaparsec per year. So that's quite a bit. Most models that I see of primordial black holes, it would be a background, but it lived comfortably under this, so it wouldn't obscure them. Okay. That's all I wanted to say about cosmology. If there's more questions, you should hit me now. Now we're going to transition to fundamental. Cosmology is also fundamental. I don't know. We're going to transition to general relativity. Okay. Cool. So the second half of my talk is about probing GR, general relativity in the strong field. So I motivate this by asking a classic question. This comes from Katz, mathematician, who asked in the mid-20th century, can you hear the shape of a drum? And the answer is obviously yes, I can tell what a percussionist is using. But what he meant as a technical question was, if I have a membrane with a boundary and I calculate its spectrum, is that spectrum unique? That is to say, if I told you what the eigenfrequencies of the drum were, could you work out the boundary? And the answer turned out to be no. You can go on Math Overflow. These are two different drums that have the same eigenspectrum. Oh well, too bad. But you'll notice they all have kinks in them. If the boundary is smooth, in fact, there is a unique mapping from the boundary to the spectrum. Okay, so that's kind of cute. We're going to try to do the same thing with black holes, but first I want to detour through quantum physics. You certainly can see the shape of a hydrogen atom. Right? This is classic, like late 1800s, early 1900s, atomic spectroscopy. Right? There is the Rydberg constant, and then the 1 over n squared law for the wavelengths of transitions in the hydrogen atom, right? This piece here comes from the hydrogen structure. It's like measuring, it's a combination of h bar and the mass of the electron, mass of the proton, fundamental constants, but you could think of it as that's the structure of hydrogen. And then the relationship, the 1 minus 1 over n squared part, that's a quantum mechanical calculation, just relating successive energy levels to each other. So if you knew this, you could measure one of these frequencies, and it gives you the Rydberg constant. And the rest of the frequencies could be, and in fact are, a sensitive test of quantum mechanics, right? Do the hydrogen lines land in the right place? Yes, modulo fine structure and hyperfine structure, there's a lot of perturbations to this. But, this is basically seeing the shape of a hydrogen atom, right? That's atomic spectroscopy. Let's do it for black holes. So here's a video of black hole merger. Hope that this will play. Okay, so here's a video of black hole merger. Its properties are very much like GW 150914, but never mind that. It's basically equal mass, nearly non-spinning. And we're zooming in on the last few orbits. So here's the black holes. They have a horizon. You can see that the gravitational potential gets quite steep near them. And they're spiraling around each other, and the gravitational waves are coming off here. And they're getting closer and closer and closer together. And in a minute, the movie's going to slow down when they get very close, when they get to sort of their very last orbit. That's coming right about now. There we go. So the movie slows down, and you can see at this point, they're still isolated black holes. If you shot a photon between them, it could get out. But there's a moment when the horizons merge, and the binary black hole becomes a black peanut. That is, you can think of that as a very highly perturbed Kerr black hole. And the last part of this movie, these last sequence of gravitational waves, are just the black peanut radiating away its essential peanutness and settling down to a Kerr black hole. Well, you can calculate with pen and paper, though you'd better bring some coffee, you can calculate the frequencies of perturbations, right? The normal mode frequencies of perturbed Kerr black holes. If I hit a black hole with a hammer or with another black hole, it rings at discrete frequencies. Now they're not normal modes, they're quasi-normal modes because the system's radiative. So you excite it and the mode damps away. So the frequencies are complex. They have a real part that's oscillatory and an imaginary part that's a damping time. Okay? And this was first done in the 70s for a Schwarzschild black hole. And then Bill Press did a numerical calculation for Kerr, and then famously Saul Tucholsky and Press and Tucholsky calculated the modes of a Kerr black hole in 1973. So last year was the 50th anniversary. And then Detweiler in the 80s coined the term black hole spectroscopy. And there's been a whole, vast literature on this topic leading up to the present day. But the idea is that a Kerr black hole has two free parameters, a mass and a spin. It's charge too, but charges aren't important in astrophysics. Okay, so it has a mass and a spin. A Kerr mode has a frequency and a damping rate. You measure one mode from a perturbed Kerr black hole, you measure the mass and the spin. GR predicts the frequencies and damping rates of all the rest of the modes. So if you want to hear the shape of a black hole, you just got to get a couple normal modes from the ringdown. Now that was thought until this paper in 2019 to be quite challenging because of course this calculation is done in linear perturbation theory. Weak perturbations to a Kerr black hole. That black peanut is not weak. That's an order 1 deformation to a Kerr black hole. So what was thought was, well, you got to wait a while. There's some kind of gravitational waves that come out in the merger as the peanut starts radiating away. Eventually, late here in the waveform, things are linear enough to use perturbation theory. You try to measure the normal modes here. And they're exponentially decaying, so it's quite challenging to measure them here. The thought was, oh, this is going to have to wait for the next generation of detectors, the mid-2030s. And then Matt Giesler, who was a grad student of Saul Tucholsky's, Max Isi, who's now a postdoc at CCA, and Saul and Mark Scheel wrote a paper where they showed this is a numerical simulation of GW 150914. In fact, this is the waveform that comes out of that movie that I just showed you. That's the blue part. And the dashed line here is what you get if you take the remnant black hole. Remember, this is a simulation, so you know its mass and spin, so you can calculate its perturbation frequencies. And you take the fundamental mode and the next 6 radial overtones, right? Just like in the hydrogen atom, there's n equals 1, 2, 3, 4, there's the radial eigenfunctions. So you take 7 radial modes, you adjust their amplitudes to best fit the signal right from the peak amplitude of the signal. This is the point. I mean, time is fictitious here. Time is a gauge-dependent quantity, so it doesn't really correspond quite to a time, but this gravitational wave location is emitted around the same time as the peanut forms. And yet a linear superposition of modes describes the subsequent emission to about a part per million. Where did the nonlinearities go? I don't have enough time to spend on this in this talk, but this would be a whole talk in itself. There's a huge amount of active research right now to try to understand why this linear picture for the radiation works so well when the space-time is manifestly nonlinear. And some people think it's a trick, just got lucky. Other people think it's a deep property of black holes. I think the jury is still out. Nobody really understands this in a deep way theoretically, but I'm an observer. This is numerical relativity. This is a mode fit. It's good to a part per million. Let's go fit some modes to observe observational data, right? That's good enough for me that this is empirically true.
Is that numerical simulation like incredibly expensive to do?
Actually, this one is not that expensive. Now, this would consume a couple days on a cluster node with 128 cores or something.
So I don't understand why people are asking, is it lucky or not? Like, it seems like you can go across a huge range.
We now have of order 1,000 simulations. In some of them, the fit is not part per million, it's part per 1,000. But in all cases, it's way better than our current observational uncertainties, which are at the 5 or 10% level. So as an empirical question, this is settled. The theoretical understanding is still, what if we had a really extremal black hole? Like, is this, violated logarithmically as the spin approaches 1? All of those things are still very much open questions. For the observers in the room, let's just run with this. Okay, so I'm gonna skip ahead. Here is GW 150914, the very first black hole merger ever. And Max and me and some other folks, Saul and Matt Giesler and Mark Scheel, and went and looked for 2 and 3 radial modes in GW 150914, and we found them. So here, the orange is the Livingston detector, the one in Louisiana. The blue is the Washington State detector. The solid lines here are the waveform that's recorded. The dashed line is the fundamental mode, the one that lives the longest. The dotted line is the first radial overtone, which decays faster. And you can see that the modes combine, to produce the total signal. There's a high amplitude of the first overtone, and then it decays away, leaving behind the fundamental. And the statistical significance of the detection of the overtone was somewhere in the neighborhood of 3 sigma. Okay, so, we're not finding a new particle here. We expect overtones. So depending on what you want to think, that's either great, we've seen it pretty much for sure, or you need 5 sigma to claim a detection, so go away. I don't know. But anyway, the statistical significance of the overtone is 3 sigma. And you can use the fact that you now see 2 modes to ask, suppose I perturb the overtone's frequency and the overtone's damping rate away from GR. How consistent is that in the data? And this is what you get. GR is totally consistent. This is like the 90% contour, so nearly the 2 sigma contour. In terms of the frequency measurement, we have GR to plus or minus 20%. Okay. That's, not exactly precision spectroscopy, but we're just getting started here. There's a lot more black hole mergers. Let's look at some other ones. So this is GW 190521. This system is the most massive system we have seen to date, and we think that its spins were tipped over. So the 2 black holes were highly spinning, and rather than having their spins aligned with the orbit, their spins were in the orbital plane. That leads to a lot of precession and produces some interesting mode structure. if you think about how this looks, here is a non-precessing system, so two black holes whose spins are aligned with the orbital angular momentum. When they merge, the Kerr remnant will have a spin that's also aligned with the orbital angular momentum. So they will produce a nice equatorial peanut-like perturbation. This is a system like 1905-21. The spins are in the plane. The orbit is like this. The remnant's angular momentum is the sum of these three things. So the remnant looks like this. If you're in the frame of the remnant, the peanut is tilted. If you think about spherical harmonics, a peanut looks like a 2-2 spherical harmonic when it's in the equator. When it rotates, it becomes a mixture of 2-2, 2-1, and a little bit of 2-0, depending on how much you rotate. So in this system, we didn't say this before we saw it in the data, we say it after, but in this system, we might expect there to be some 2-1 excitation. And in fact, Harrison Siegel, who's a grad student at Columbia, working with us in our group at CCA, indeed found that the frequencies that you detect when you fit damp sinusoids to this system match the predicted 2-2 and 2-1 frequencies from the estimated mass and spin that we get by looking at the whole waveform instead of the ringdown. So it looks like this was a tilted excitation of the remnant black hole that excited the 2-1 and the 2-0 modes, and maybe also the 3-2 mode for good measure. If you use that to perform a test of GR, if you use the 2-2, if you perturb the 2-2 mode relative to the 2-1 mode, you get something that's consistent with GR, but not a great measurement. If you perturb the 3-2 mode relative to those other modes, you see the frequency is constrained to about 10%. So overall, this is yet another 10 or 20% confirmation that the modes are in the places that GR would say they are. And then, because we saw it in the data, we went back and looked at numerical simulations. Here's a smattering of numerical simulations. On the y-axis here is plotted the amplitude of the 2-1 mode versus the 2-2 mode. On the x-axis is plotted the misalignment angle between the orbit and the remnant spin. And the black line here is just the ratio of Wigner D's for the 2-1 excitation versus the 2-2. So it's literally just the rotation matrix of the spherical harmonics. And the actual mode amplitudes match very well with the expectation from simply rotating a 2-2 perturbation into the misaligned remnant frame, which is pretty sweet. The little bit of scatter here matches the sort of kick velocity, which has to do with above and below the orbital plane asymmetries in the initial setup. So it's not really accounted for in this simple rotational picture, but the rotational picture gets most of the variation that you see here. And in fact tells you that just like we saw in 1905-21, sometimes you can excite the 2-1 to amplitudes that are higher than the 2-2, which is not something that people had considered before. We were very surprised when we first saw that in the data. And now we think we understand why you might have a 2-1 mode that's excited at higher amplitudes than the 2-2. You can read the paper on the archive if you want to see it. Yeah.
There's like a jump in the top, right? Is that something?
Yeah, these systems, it's not shown on this plot in the color scheme. These systems are high mass ratio systems, and they have a lot of 2-1 for other reasons as well. Like when the systems are not close to equal mass, they don't have this exchange symmetry that I was talking about with the grad students, so they don't naturally prefer even modes. And so they're kind of anomalous, but we think we understand why. These systems are all close to equal mass.
And that wouldn't be described as.
Yeah, that would be like this plus the extra excitation that you get from the unequal mass ratio. There's another plot that I didn't put on this screen, but that predicts that quite well as well. Okay, so, this is a young field. We've analyzed these two systems in detail. There's only 68 more to go. We're collecting them by the hundreds. We're working towards sort of industrializing this process, but in terms of spectroscopy, this is where we are. It's like 1700s chemistry where you throw sodium in the lamp and it turns yellow or whatever. But one day, I think, we will be here with black hole spectroscopy, and if you stack enough of these measurements on top of each other, 10% becomes 1%. And that is, I would argue, a real precision test of whether the Kerr metric is the right description of astrophysical black holes. And I'm gonna stop there and take any more questions. Yeah.
So there's some crazy ideas about black holes where the thing that's modified is really the event horizon and not the light ring.
Yeah.
So when you talk about these quasi-normal ringdowns, those are really probes of the photosphere of the light ring.
That's right. The horizon changes are sort of exponentially suppressed depending on exactly how far outside the horizon you want to modify things.
Or they come out much later than the ringdowns.
Yeah, if you put a barrier, a firewall or whatever, you get an echo that can come out much later.
So are those things that you search for as well?
Not me personally, but those are things that are searched for. There have been a couple of claims of echo detections at somewhat marginal significance that I think largely haven't totally held up. But absolutely, that is something that people look for. And if we ever saw a smoking gun of a time reversed signal that came out 10 milliseconds after the ringdown phase of one of our black holes, that would be phenomenal, because it would tell you that there's a pretty reflective boundary condition instead of the horizon.
I guess one follow-up to that is this question of why linear perturbation theory works so well. It's not, we're saying it's very nonlinear, which is true in one sense, but on the other hand, the curvature is extremely weak in units of light length.
Yeah, no, that's right.
So it's not that there's really strong gravity in that sense. I thought about the light ring.
No, we're absolutely not probing long scale anything. But if you wrote a Kerr background and expressed this metric, I know it's all gauge dependent, but you wrote this metric as Kerr plus delta. Delta would be order 1, right? Large. That's the sense in which I mean that it's nonlinear, and that works even if you use gauge invariant quantities, like you look at the various algebraic scalars in the spacetime or whatever. They're quite far from Kerr. Gauge invariant measures of non-Kerrness inside the light ring are order 1.
And if you just, I think you had 7 free parameters or something, because there were 7 modes.
Yeah.
These amplitudes you fit. If you take a signal like that, which doesn't have that many features in it, right? It's more or less a real and imaginary part or something. And then you fit it to a template with 7 parameters. Is an accuracy of 1 in 1,000 or 1 in a million really that surprising?
It's a little bit surprising. And so I skipped over this slide, but they asked themselves exactly that question, right? So this is the mismatch that you get. So this was the sort of part per million or maybe 10 parts per million that happens if you use the right 7 modes. So here they have made the mode frequencies the correct mode frequencies, and you can see the mismatch just keeps on going. Here they have perturbed a mode frequency by 1%, and it peters out, by 5%, by 20%. So it's not simply, I've got a lot of free parameters, I'm fitting an elephant's trunk, It's, in that sense, the fit is fairly robust. In other senses, overtones beyond 3 or 4 are not terribly well measured. So there's another sense in which you could talk about, in order to be a mode, it needs to be something that is constant amplitude, oscillatory. Right? The decay happens, but if you reference them all at the same time point, the amplitudes need to be stable. If you fit at different start times, these mode amplitudes are stable. But like the 5, 6, and 7 overtones, their amplitudes jump around a lot before they finally just vanish. Once you get past the second overtone, the quality factor of the mode is less than 1, so they don't even do a cycle. They're just increasingly steep death. And so I don't think anyone has a firm ontological commitment to these things actually being oscillating modes that are clearly observed in this NR simulation. Again, for the test of GR, this is not really necessary, but that may also play a role in this question about nonlinearities.
Here you focused on black holes, but I heard that when you look at the mergers of neutron star in Illinois and you can also say something about the equations of state.
You can.
So how does it work?
There's two ways that you learn about the equation of state. The easiest way, since neutron stars, they're extended physical bodies, they feel tides. And so the potential of one raises a tide on the other, and that modifies the potential, which modifies the orbit, which is detectable in the orbital phase. The way we organize these effects is in a series expansion called post-Newtonian series, which is an expansion in V over C. The 0th post-Newtonian order is the first, the quadrupolar emission formula that you might have seen or heard about gravitational radiation. The half PN order is the next, the 1 PN, unfortunately, is V over C squared. So a half is V over C and then V over C squared, etc. Tides enter at the 5th post-Newtonian order. Waveforms have been calculated pen and paper through 3.5, but not 4, which is actually a time shift. There's a logarithmic term at 4, not 4.5 and not 5. So you have to do a little bit of calibrating to make sure that there aren't GR effects at 5 PN that are messing with your tidal signal. But in principle, these linear tides induce changes in the orbit that can be measured in the phase. That's particularly prominent above maybe 500 or 600 hertz for most equations of state. And that reflects back on the equation of state, I should have said, because the degree of stretchiness of the star, right, the degree to which it's perturbed depends on its radius, which is sensitive to the equation of state, and also the density profile within the star, which is sensitive to the equation of state. So by making these tidal measurements, we hope to constrain equation of state parameters. Another way, which is at present not been observed, but should be possible in the next generation of detectors, is when the neutron stars actually slam into each other, something very dynamic happens, and that itself radiates gravitational radiation. So you see the in-spiral terminate and turn into a burst of some sort of oscillatory power at the oscillation modes of this hypermassive neutron star. So you can look for bursts of radiation in the sort of 1 to 2 kilohertz frequency that tell you about the structure of that slammed together remnant, which also relates to the equation of state.
If all I wanted to do was measure the expansion rate h of z,
Yep.
and I gave you an infinite amount of money, would this ultimately be the best way to do it, or competitive, or how do I kind of fit this into the sort of ensemble of?
At which redshifts do you want to do it?
You tell me. I mean,
Okay.
Yeah, you tell me.
So if you wanted to do it for redshifts that are, say, less than 1, I would say you should build the next generation of gravitational wave detectors, which will cost $1 billion or $2 billion. They can see neutron stars to redshift 2. And you should build many wide field of view 30-meter optical telescopes that can slew rapidly so that you can catch counterparts to redshift 2. And then you can do the easy mode measurement where gravitational waves give you the distance, observations of the host galaxy give you the redshift. Each of those instruments that I have discussed is of order $1 billion. So that's an expensive way to go. If you want to measure redshifts beyond 2, then yes, I would spend the money on this because black holes are probably the best source we've got going at those distances when galaxies are starting to peter out. So it doesn't even matter how hard you look for them, just running out of numbers.
Sorry, can I ask her
Yeah.
a follow-up stupid question? Why do they need to slew quickly? If you know where the merger came from, don't you have all
Yeah,
the
they
time
don't
in the
need to
world
slew that fast, actually. They just need to be interruptible. So you can't have, like, I don't know, some dopey exoplanet scientist or something who's sitting on the telescope that night. We caught 17817, the flash, the dot was seen 6 hours after the merger.
But sorry, do you need do you need the EM spectrum from the event or from the host galaxy? Because the host galaxy
No,
is
you
always
just
gonna be
need to
there.
see the bright thing. But it fades, the kilonova fades pretty quickly.
Oh, so you need to know because the bright thing tells you which galaxy it came
Tells
from.
you which galaxy to look at. So, I mean, with that sized telescope for something that goes off at redshift 0.5, you have a week to see the bright dot. So, no, you don't need it to slew onto target rapidly, but you need it to be interruptible. So you need to make sure that you have a high priority which you would. Anyway, to get out to redshift 2 with kilonova, though, you need pretty big class. At 35 megaparsecs, the number to remember is it peaked at about 16th magnitude in the P band.
Well, that means so much to me.
Maybe just a short conversation about the next generation and Einstein telescope and this program, because people would be interested probably.
Yeah, I'll flash up that. Right, so because we measure amplitudes, right, we like sensitivity improvements, rapidly produce volume improvements. The picture in the United States for the next generation is a concept called Cosmic Explorer, which is another Michelson interferometer, but instead of 4-kilometer arms, it has 40-kilometer arms. Since the gravitational field is a strain, 10 times the arm means 10 times the signal. Okay, so even if you put the same kit in it, the signal's gone up by a factor of 10, the noise level stays the same, you win by a factor of 10, and that's enough to get you out to the edge of the universe, basically. The challenges there, the big expense, is a site that you can have 40 kilometers of vacuum at 10 to the minus 11 torr. So you need lots of fancy pipe. You may need to dig a trench because the laser goes straight, but the Earth's surface curves. So there's a lot of engineering challenges in constructing this. As long as you're going to invest the money in that, you might as well also improve the optical setup. So the concept has higher power lasers and more of this squeezing and, advances in that direction as well. But the fundamental thing is it's just 10 times bigger, so it gets 10 times more signals for most improvements. The European concept is called Einstein telescope, and it is trying to address principally this low frequency noise here, which is largely ground motion. So the slope of this curve here is something like f to the minus 8. In amplitude it's f to the minus 4. In power it'd be f to the minus 8. Because the mirror is hung from a pendulum, which is hung from a pendulum, which is hung from a pendulum, which is hung from a stable platform. And they all have very low resonant frequencies. So the response of a pendulum above its resonant frequency falls off like 1 over f squared times f squared times f squared times f squared. That apparatus is pushed about as far as it can go in LIGO. It turns out that most of the motion, the seismic motion of the ground, is actually in surface waves. So the Europeans said, we'll just bury it. We'll take an interferometer now of slightly smaller, kilometers, 10-kilometer scale, and we'll put it inside a mountain. And then all the seismic waves are gone, and this low frequency noise is reduced without having to go to 40-kilometer long arms. So that's the Einstein telescope concept. They're pretty comparable in terms of sensitivity. There's technological trade-offs between the two. They're pretty comparable in the end in terms of expense. Both gravitational wave communities would like to build the instrument. Neither of them is fully funded at this point. So we'll see what happens. Ideal would be to have an Einstein telescope in Europe, 2 cosmic explorers in the US. If Australia wants to build another cosmic explorer, that'd be pretty sweet. Ideal would be having all of these at once. It would be a shame if none of them got built. We're currently going around hat in hand to funding agencies to try to collect $1 billion to make this happen. That's the picture. But they see neutron stars to redshift 2, which means a couple million neutron star mergers a year. They see black holes to redshift as high as you want, so another 250,000 or 500,000 black hole mergers a year. It's really insane. So kind of the first time you can literally see everything that's happening in the universe.
So how come seismic events don't become more important as the thing gets bigger?
They become marginally more important, but the suspension is the same. So the absolute swinging of the mirrors doesn't change because there's 40 kilometers arm down here. Small seismic events happen all the time. Anything, I don't know the actual magnitude limit, is somewhere around 4 or 5. They actually have to put the interferometer in locked mode because an earthquake at magnitude 5 will excite such vibrational modes in the hanging mirror that it'll take a few days to damp out. So you either like clamp down the interferometer, let the earthquake pass, and then let it go again, or you lose a week. But that's not like destructive to the instrument or anything, and those happen rarely in the sites that have been chosen.
I don't know whether people, but there's the drinks and reception down on the.
Yeah, right.
Is it on the 8th floor, is it?
It would be on 8th if it
Is it normally, I mean, that's where it used to
Normally
usually
it's-
be. but
normally it's where it
sometimes
is.
on the 10th. Okay,
I was
wanna
told
send
where to
people
go.
Oh, okay.
We'll see if that matches. I mean, I'm just gonna follow everybody, but
If people are up for waiting another 30 seconds, we might address another topic, which is if you have a million neutron star mergers as a background,
right.
what else can you do?
Oh, there's a paper appearing on Archive today that I'm on from Katerina Hatzionu and a postdoc of hers and me. You can actually hope to do quite a lot. And the reason is that you don't just care, I took out the spectrogram, okay, here. You care about both times and frequencies. So, here's a merger signal, say a neutron star merger. It starts at low frequency with the orbit well separated. Gradually, the orbit decays. As the objects get closer, the emission goes up, so the decay happens faster and faster and faster and faster to run away. Okay. There's a neutron star merger in the universe about every minute, maybe every 30 seconds, something like that. That's the rate we've estimated so far. In Cosmic Explorer, this process, from when it first enters a sort of sensitive band to here, is 90 minutes, 3 hours, something like that. So soon thereafter, there will be another neutron star merger. And then maybe there will be a little bit heavier neutron star merger that appears and goes a little quicker, right? So this looks bad.
Yeah, right.
But all you care about is where these tracks cross. So if you ask, how long does this system spend at one frequency? So let's blow up this region here. Right? It's very slowly evolving in frequency. So this is like zooming in there. Here it goes. It's doing its churn.
Because the reason you care about why it's crossing is that tells you there's two. Is that the point?
That's right.
Uh-huh.
If they don't cross in time frequency space, they don't interfere with each other. So what you want to think about is you want to draw, there's a Heisenberg uncertainty principle, right? Which says that this pixel size in your data analysis has to satisfy delta t, delta f is bigger than a half. But consistent with that, you want to draw the tightest pixel you can around the neutron star track. So here you draw long time, narrow frequency resolution pixels. Here you draw short time, long frequency resolution pixels. And then you have to ask yourself, will there be another neutron star signal in this pixel? And if you calculate that density all the way down to 5 hertz and maybe even 1 hertz, the occupation number per pixel is way less than 1. So there will be many neutron stars in the interferometer at one time, but they won't be interfering with each other in time frequency space. There's been a lot of confusion
Basically, you
on
can
this,
just
but-
analyze them totally separately and localize
Yeah.
them.
Yeah, so you can treat those as totally separate. And then these rare crossings you do have to account for, but it's much less than a pessimistic picture where, oh my God, there's 1,000 neutron stars at one cycle, what do I do?
Right. Well, thank you again.
Yeah, thank you very much.